Picture this: a universe where every star you see tonight will one day vanish, where time itself might stop, and where the very fabric of reality could tear apart. What if I told you that the fate of everything, our galaxy, our planet, even the atoms that make us who we are, is already sealed by forces beyond our control? The universe is not eternal. It has an expiration date, and scientists have narrowed it down to three terrifying, awe-inspiring possibilities: the Big Freeze, the Big Crunch, or the Big Rip. One will turn the cosmos into a frozen graveyard of dead stars. Another might collapse everything back into a single point, like a cosmic reset button. And the last, it could shred galaxies, planets, and even the laws of physics in a violent, unstoppable end. This isn't science fiction. It's the real story of how everything ends. And today, we're diving deep into the science, the timelines, and the mind-bending theories that predict the ultimate fate of existence itself. Stick around, because by the end of this journey, you'll see the universe in a way you never have before. Now, let's take a closer look at the first of these cosmic endings, the Big Freeze, also known as the heat death of the universe. Imagine a campfire burning bright on a cold night, its flames dancing and crackling with energy. But as the hours pass, the fire slowly dims, the embers fade, and eventually, all that's left is a pile of cold ash. The Big Freeze is the universe's version of that dying fire, an inevitable, slow fade into darkness. Here's how it happens. Right now, the universe is expanding, and not just at a steady pace, it's accelerating. This expansion is driven by something called dark energy, a mysterious force that pushes galaxies apart faster and faster. Over time, this relentless stretching of space has chilling consequences. Stars, the engines of light and heat in the cosmos, will eventually burn through their fuel. One by one, they'll flicker out, leaving behind cold, dead remnants like white dwarfs and neutron stars. Even those will decay over trillions of years as protons, the building blocks of matter, break down into nothingness. As the universe expands, matter spreads thinner and thinner, and temperatures plummet toward absolute zero. This is the concept of entropy, nature's way of saying that energy disperses and becomes unusable over time. Think of it like a cup of hot coffee left out too long. No matter how hot it starts, it will eventually cool down to room temperature, its heat lost to the air around it. In the Big Freeze, the entire universe becomes that lukewarm coffee, with no heat left to stir motion or life. The final stage is a cosmos so vast and empty that even black holes, the last survivors, will evaporate away due to a process called Hawking radiation. What remains? A silent, infinite void, no light, no heat, no structure. Just an eternal freeze where time itself may lose all meaning. So why does this matter to us? Because the Big Freeze isn't just a distant possibility. It's the most likely scenario based on what we know today. And while it might seem bleak, it's also a humbling reminder of how fleeting even the grandest cosmic events are in the face of time's unstoppable march. But don't worry, this isn't the only way the universe could end. Next, we'll explore a scenario where the cosmos doesn't fade away but collapses in on itself. The Big Crunch is coming, and it's a whole different kind of ending. Now, let's pull back the curtain on the science that makes the Big Freeze such a compelling possibility. At the heart of this cosmic chill is dark energy, the enigmatic force pushing the universe apart. Picture a balloon being inflated faster and faster. Dark energy is the unseen hand on the pump, accelerating the expansion of space itself. Scientists estimate dark energy makes up about 68% of the universe's total energy, dwarfing even the gravitational pull of dark matter. This dominance means galaxies aren't just drifting apart, they're being actively shoved, stretching the fabric of space-time to its limits. But expansion isn't the only player here. The second law of thermodynamics seals the universe's fate. This law states that entropy, or disorder, always increases in a closed system like our cosmos. Imagine shaking a box of puzzle pieces. They'll never spontaneously form a complete picture. Similarly, the universe's energy will keep dispersing until it's evenly spread, leaving no concentration of heat or motion to sustain life. Every star that dies, every particle that drifts farther away, is another step toward this equilibrium of absolute stillness. Then there's proton decay, the ultimate eraser of matter. Protons, the sturdy building blocks of atoms, were once thought indestructible, but modern physics suggests they might not last forever. Over timescales so vast they're almost unimaginable, think 10 to the power of 34 years, protons could disintegrate into lighter particles. If this happens, even the remnants of dead stars and planets would vanish, leaving behind a sea of subatomic haze. No atoms, no molecules, just a thin soup of particles too sparse to form anything meaningful. The interplay of these forces paints a stark picture. Dark energy stretches space-time beyond recognition. Thermodynamics ensures energy becomes unusable, and proton decay dismantles matter itself. Together, they orchestrate a finale where the universe doesn't just grow cold, it becomes incapable of change, a fossilized relic of its former vibrancy. Yet, as eerie as this sounds, it's a testament to the delicate balance of physical laws that govern everything from galaxies to grains of sand. And while the Big Freeze might be the leading theory today, the cosmos always has surprises in store, like the dramatic counterpoint we'll explore next, the Big Crunch. Now, let's take a journey through time to see how the Big Freeze unfolds step by step. Picture the universe not in billions, but in trillions of years, a timescale so vast it's almost beyond comprehension. The first major milestone comes roughly 100 trillion years from now, when the last stars flicker out. By then, the universe's gas reservoirs, the raw material for new stars, will have been exhausted. No more stellar nurseries, no more glowing giants lighting up the cosmos. The galaxies, once vibrant with light, will become graveyards of dead stars, their embers slowly fading into darkness. But even in this twilight era, remnants of activity remain. Brown dwarfs, failed stars too small to ignite fully, might still collide occasionally, sparking brief, dim flares. And the corpses of stars, white dwarfs, will cool over eons, turning from faint white to deep red, then finally to invisible black dwarfs. Yet these events are mere whispers in the growing silence. Fast forward even further, and the universe enters the era of black hole dominance. With no new stars, black holes become the last structures of consequence. They'll feast on the occasional stray star or gas cloud, but even their reign has an expiration date. Thanks to Hawking radiation, these cosmic monsters slowly lose mass, evaporating over unimaginable timescales. The smallest might vanish in a mere 10 to the power of 67 years, but the supermassive ones at the centers of galaxies, they'll cling on for 10 to the power of 100 years before finally dissolving into a puff of particles. Beyond this point, the universe enters its final, featureless phase, heat death. With no stars, no black holes, and no concentrated energy, space becomes a uniform sea of faint radiation. Any remaining particles are so spread out they might as well be alone in the void. Proton decay, if it occurs, will erase the last traces of matter, leaving only photons and leptons drifting endlessly. Time itself may lose meaning, as there are no events left to mark its passage. No motion, no change, just perfect, unchanging equilibrium. This isn't just a distant abstraction. Each stage reflects the relentless laws of physics playing out on cosmic scales. From the last star's death to the evaporation of black holes, the Big Freeze isn't an abrupt event, but a slow, inevitable unraveling. And while it might sound bleak, it's a reminder of how finely tuned our universe is for now. We exist in a golden age of light and structure. But as we'll soon see, there are other ways the cosmos might meet its end, and some are far more violent than this quiet fade to black. Now let's shift our focus to the most pressing question of all. What does the Big Freeze mean for life? It's one thing to chart the universe's cold, slow decline, but another entirely to ask whether anything or anyone could endure it. The short answer: it's a staggering challenge, but not necessarily an impossible one. Imagine a civilization advanced enough to outlast the death of stars. By the time the universe enters its twilight, any surviving beings would need to harness energy sources beyond anything we can conceive today. One far-fetched yet tantalizing idea involves black holes. These cosmic giants, though destined to evaporate, could serve as power plants for unimaginably long timescales. A society might extract energy from a black hole's rotation or even its Hawking radiation, stretching their survival into the era of darkness. It's a concept that feels ripped from science fiction, but physics doesn't outright forbid it, just demands ingenuity on a scale we can barely fathom. Then there's the Boltzmann brain paradox. In a universe teetering toward maximum entropy, random quantum fluctuations could, in theory, spontaneously create a self-aware entity, a lone mind materializing from the void, complete with false memories of a past that never was. It's a haunting thought experiment, suggesting that even in the emptiness of heat death, fleeting moments of consciousness might flicker into existence. But here's the catch: these brains would be isolated, ephemeral, and utterly devoid of meaning, hardly the stuff of a thriving civilization. Philosophically, the Big Freeze forces us to confront the fragility of existence. Our universe's golden age, the brief epoch where stars shine and life can arise, is just a blink in cosmic time. If civilizations don't find a way to transcend entropy's grip, all knowledge, art, and discovery will eventually be erased by the unrelenting march of thermodynamics. Some thinkers argue this inevitability lends urgency to humanity's ambitions. If we're to leave any lasting mark, it must be through feats that outlast even the cosmos itself, perhaps by creating new universes or encoding our legacy into the fabric of reality. Of course, all of this hinges on unknowns. Could life adapt to near absolute zero? Could we master energy harvesting on cosmic scales? The answers lie at the edge of speculation. But the very act of asking these questions reveals something profound. Even in the face of an inevitable freeze, the human drive to explore, persist, and imagine refuses to surrender. And as we'll see next, not all cosmic endings are so quiet. Some are explosive enough to rewrite the rules entirely. But let's turn the page to a cosmic scenario where the universe doesn't fade into cold silence. It collapses in on itself in a fiery finale. This is the Big Crunch, the dramatic counterpoint to the Big Freeze. Picture the universe's expansion hitting the brakes, not because it runs out of energy, but because gravity, the same force that holds your feet to the ground, wins the ultimate tug of war. Instead of spreading endlessly, galaxies begin rushing toward one another, space itself shrinking like a balloon deflating. The end result: everything, every star, every atom, even space-time, gets crushed back into a single scorching point, a mirror image of the Big Bang that started it all. Gravity's victory hinges on a cosmic balancing act. Right now, dark energy is pushing the universe apart. But if there's enough matter and dark matter out there, their collective gravity could eventually overpower that expansion. Think of it like rolling a ball up a hill. If the ball doesn't have enough speed to escape the hill's pull, it rolls back down. For the Big Crunch to happen, the universe's total density must cross a critical threshold, tipping the scales from forever expanding to collapse imminent. Scientists call this a closed universe, where space curves back on itself like the surface of a sphere. The journey toward the crunch would be both spectacular and terrifying. As galaxies merge, the night sky would blaze with collisions, birthing new stars briefly before temperatures soar. Eventually, the cosmic background radiation, the faint afterglow of the Big Bang, would grow hotter than the surfaces of stars, cooking any surviving worlds. Atoms themselves would unravel as forces holding them together are overwhelmed, reducing all matter to a primordial soup. the final moments, a singularity hotter and denser than anything in existence today, possibly triggering a new Big Bang and restarting the cycle. What's fascinating is the possibility that our universe could be part of an endless loop: bang, expansion, crunch, repeat. Some theories suggest each cycle might tweak the laws of physics slightly, meaning a future universe could have different constants, particles, or even dimensions. But here's the catch: for life to persist across cycles, civilizations would need to survive the crunch's inferno or encode their essence into something that outlasts it. Unlike the lonely, frozen eternity of the Big Freeze, the crunch offers a strange kind of hope, an end that's also a beginning, yet the verdict isn't in. Current evidence suggests the universe's expansion is accelerating, making the crunch less likely. But in a cosmos full of mysteries, gravity might still have a few surprises up its sleeve. And as we'll soon see, there's a third fate even more violent than the crunch one, where the universe doesn't just collapse, but shreds itself apart. Now, let's pull back the curtain on the science that makes the Big Crunch more than just a dramatic idea. At the heart of this cosmic collapse lies a delicate balancing act between two titanic forces: the outward push of dark energy and the inward pull of gravity. For the universe to eventually reverse its expansion, it must first reach something called critical density. Picture this as the universe's tipping point, the exact amount of matter and energy needed to halt eternal expansion and start the great cosmic contraction. Critical density isn't just a random number. It's calculated based on how fast the universe is expanding right now and how much gravity exists to counteract it. Here's where dark matter becomes the unsung hero or villain, depending on how you look at it. While invisible and mysterious, dark matter's gravitational influence is profound. Combined with ordinary matter, it could provide enough cosmic weight to eventually overcome dark energy's repulsive force. Think of it like a seesaw. If dark matter and regular matter together outweigh dark energy's push, the universe eventually stops expanding and begins collapsing in on itself. This brings us to the concept of a closed universe, one where space curves back onto itself like the surface of a globe. In such a universe, if you could travel far enough in one direction, you'd eventually loop back to where you started. This geometry is key to the Big Crunch scenario because it means gravity has the upper hand. Contrast this with an open or flat universe where space stretches infinitely or remains balanced on a knife edge between expansion and collapse. In those scenarios, dark energy dominates, leading to the Big Freeze, a slow, cold fade into nothingness. Current observations suggest our universe is remarkably close to flat, with just enough matter and energy to keep expansion going, but not so much that it guarantees a Big Crunch. Yet the margin is razor thin. If future discoveries reveal even slightly more matter or dark matter than we've accounted for, the scales could tip. That's what makes the Big Crunch so tantalizing. It's not ruled out, just hanging in the balance. The difference between these fates comes down to numbers we're still trying to pin down, like the exact behavior of dark energy over time. If dark energy weakens as the universe ages, gravity might yet have its day. But if it strengthens or stays constant, the Big Freeze remains the more likely outcome. Either way, the science behind the Big Crunch reminds us that the universe's fate isn't set in stone. It's a cosmic equation still being written. Now, let's fast forward to the moment gravity finally wins the cosmic tug of war. The Big Crunch wouldn't happen overnight. It would unfold over billions of years, with the universe reversing its expansion in stages. First, galaxies would begin drifting closer together, pulled by the growing dominance of gravity. Picture a cosmic traffic jam, where clusters that once raced apart now slow down, stop, and start moving toward one another. Over time, these galactic collisions would become more frequent, merging into supergalaxies as the universe's breathing space shrinks. As the contraction accelerates, temperatures would rise dramatically. The cosmic microwave background, the faint afterglow of the Big Bang, would heat up from its current frigid -270 degrees Celsius to something far warmer. Stars once scattered safely apart would crowd together, triggering explosive novas and supernovas. The night sky, instead of being dotted with distant, twinkling lights, would blaze with the light of countless stars crammed into a shrinking cosmic neighborhood. Eventually, even atoms would feel the squeeze. In the final stages, the universe would become a pressure cooker, with temperatures and densities soaring to levels unseen since the Big Bang itself. Planets, stars, and black holes would all merge into a superheated soup of particles. Space itself would warp and crumple, collapsing back toward a singularity, a point of infinite density where the laws of physics as we know them break down. But here's where things get even more fascinating. Some theories suggest the Big Crunch might not be the end. Instead, it could be a reset button. If the singularity rebounds just as it did during the Big Bang, we could be looking at a cyclic universe where expansion and contraction repeat in an endless loop. Imagine a cosmic heartbeat, with each crunch birthing a new universe in the next bang. While this idea remains speculative, it offers a poetic alternative to the finality of other scenarios. Of course, whether the universe cycles or ends for good hinges on details we're still uncovering. Would the singularity rebound cleanly, or would it simply fizzle out? Could information from one cycle survive into the next? These questions push the limits of our understanding, blending physics with philosophy. For now, the timeline of the Big Crunch remains one of cosmology's most dramatic what-ifs, a slow-motion collapse that could either erase everything or set the stage for a brand new beginning. Now, let's shift our focus to something even more mind-bending. What happens to life itself as the universe crunches? Could any form of existence survive this cosmic collapse, or would it be game over for everything? The answer isn't simple, but it's packed with fascinating twists. First, consider the environment. As the universe contracts, temperatures rise and radiation intensifies. The cozy pockets where life thrives today, like planets orbiting stable stars, would become unbearable. Imagine trying to survive in an oven that's constantly getting hotter. Early on, advanced civilizations might adapt by building shields or migrating to cooler regions, but eventually, even those refuges would vanish. Stars would crowd together, turning the cosmos into a minefield of supernovas and gamma-ray bursts. The sky, once a serene expanse, would become a lethal light show. But what if life finds a way? Some theorists suggest that hyper-advanced beings could harness the energy of collapsing stars or even black holes to power their survival. Picture a civilization so advanced that it treats dying suns like batteries, extracting energy until the last possible moment. Others propose digital existence, uploading consciousness into indestructible quantum computers that could withstand extreme heat and pressure. These ideas stretch the limits of imagination, but in a universe where physics is pushed to the brink, who's to say they're impossible? Here's where it gets even wilder. If the Big Crunch leads to a new Big Bang, a cosmic reboot, could remnants of our universe carry over into the next one? Some models hint that information, like the structure of space-time or quantum states, might persist through the singularity. It's like a cosmic game of telephone where whispers of the past universe echo into the new one. Life, in some form, might find a way to re-emerge, riding the wave of a fresh expansion. Of course, this hinges on unknowns. Would the next universe even have the same laws of physics? Could complexity arise fast enough for life to reappear before another crunch? These questions blur the line between science and philosophy, reminding us that the Big Crunch isn't just about endings, it's about the tantalizing possibility of cosmic renewal. For now, it's a reminder of life's fragility and resilience, playing out on the grandest stage imaginable. Now, let's turn to the most dramatic of all cosmic endgames, the Big Rip. Picture this: instead of a slow fade or a crushing collapse, the universe is violently shredded apart, piece by piece, until even atoms are torn to nothingness. It's not just an ending, it's a cosmic demolition unlike anything else. The Big Rip hinges on a mysterious force, phantom dark energy. Unlike ordinary dark energy, which drives the universe's expansion at a steady pace, phantom energy grows stronger over time. Imagine a car that doesn't just accelerate but presses the gas harder the farther it goes. Eventually, this runaway force would overpower gravity, electromagnetism, even the nuclear bonds holding atoms together. Galaxies would be ripped from one another first, then stars from their galaxies, planets from their orbits. But it doesn't stop there. In the final moments, atoms themselves would unravel, dissolving into a sea of disconnected particles. Timing here is chillingly precise. Current models suggest the Big Rip could unfold in a mere 22 billion years, a blink in cosmic terms. About 60 million years before the end, galaxies would start flying apart. 3 months before doomsday, solar systems would disintegrate. 30 minutes before the end, planets and stars would burst like overinflated balloons. And in the last infinitesimal fraction of a second, the fabric of spacetime itself would tear, leaving no structure intact. What makes this scenario so harrowing is its inevitability if phantom energy exists. Unlike the Big Freeze or Big Crunch, where survival might be theoretically possible in some form, the Big Rip leaves no loopholes. No matter how advanced a civilization becomes, there's no shielding against the unraveling of reality itself. Digital mines, black hole habitats, even hypothetical rip-proof dimensions would succumb. It's the ultimate checkmate, yet the Big Rip isn't just about doom. It forces us to confront profound questions. Is dark energy truly constant as we once thought, or is it evolving toward this catastrophic end? Observations of distant supernova and galaxy clusters are hunting for clues. Some scientists argue that if phantom energy were real, we'd already see hints in the universe's expansion rate. Others counter that its effects might be subtle until it's too late. This theory also reshapes how we think about time. In a Big Rip scenario, the universe doesn't just end, it ends early. Most models of eternal expansion suggest stars could glow for trillions of years, but phantom energy cuts that timeline short. It's like a cosmic hourglass suddenly smashed mid-countdown. For now, the Big Rip remains a terrifying possibility, not a certainty. But it reminds us that the universe's fate isn't just a distant abstraction. It's a puzzle we're piecing together in real time with every telescope and particle detector. And that, in itself, is a reason to keep looking up. Now, let's take a closer look at the engine behind this cosmic catastrophe, phantom dark energy. Unlike the steady push of ordinary dark energy, phantom energy behaves like an unrelenting, ever-strengthening force. Think of it as a rubber band that doesn't just stretch but grows tighter and more destructive the more it's pulled. Scientists describe it by a simple but sinister equation. Its pressure isn't just negative but becomes increasingly negative over time. This is what sets it apart and makes the Big Rip possible. At the heart of this phenomenon is Einstein's cosmological constant, but with a terrifying twist. Normally, dark energy's density remains constant as the universe expands, like a gentle breeze pushing galaxies apart. Phantom energy, however, grows denser. Imagine pouring water into a cup that never fills instead. The water starts rising faster, threatening to overflow. In cosmic terms, this means the repulsive force of phantom energy doesn't just counteract gravity. It escalates until it dominates every other force in nature. Here's where it gets even wilder. The four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, are the universe's glue. Gravity holds planets and stars together, electromagnetism binds atoms into molecules, and the strong nuclear force keeps atomic nuclei intact. But phantom energy doesn't play by those rules. Over time, its repulsive power would surpass even the strong nuclear force, which is 100 times stronger than electromagnetism. Picture a demolition crew that starts by tearing down skyscrapers, then bridges, and finally the very bolts holding steel beams together. That's phantom energy's path of destruction. First galaxies, then stars, then atoms themselves. What makes this so unsettling is the sheer scale of its reach. Gravity weakens with distance, but phantom energy's repulsion strengthens as space expands. It's like a tug of war where one side keeps adding invisible, unstoppable players. Even black holes, the universe's ultimate vacuum cleaners, wouldn't stand a chance. Their event horizons, the points of no return, would be stretched and shredded as phantom energy rips spacetime itself apart. But how do we know this isn't just science fiction? Observations of distant supernova and galactic clusters hint that dark energy's behavior might not be constant. Some data suggests the universe's expansion is accelerating slightly faster than predicted, a possible fingerprint of phantom energy. Yet, it's still a fringe idea because it defies our current understanding of quantum mechanics. Most models assume dark energy's density stays steady. Phantom energy throws a wrench into that assumption. The real puzzle lies in figuring out which version of dark energy we're dealing with. Is it the gentle kind that leads to a slow big freeze, or the phantom variety that brings a violent big rip? Right now, telescopes like the James Webb Space Telescope and upcoming missions like the Euclid satellite are racing to measure cosmic expansion with unprecedented precision. The answer could lie in tiny deviations in the light from ancient supernova or the way galaxies cluster across billions of light years. One thing's certain: if phantom energy is real, it rewrites the rules of physics in the most dramatic way possible. It's not just about how the universe ends, it's about uncovering whether the laws we take for granted have an expiration date. And that's a mystery worth chasing, no matter how unsettling the answer might be. Now let's walk through the horrifying countdown to the Big Rip, a timeline where the universe doesn't just fade, it's torn apart piece by piece. If phantom energy is real, this isn't some distant, abstract threat. It's a meticulously sequenced demolition job, unfolding over tens of billions of years, with each stage more violent than the last. The first domino to fall would be the cosmic web, the vast network of galaxies bound together by gravity. About 60 million years before the end, phantom energy's grip would overpower even these titanic structures. Galaxies like our Milky Way, held together by the delicate balance of dark matter and gravity, would start drifting apart. Picture a city crumbling not from bombs but from its very roads and bridges dissolving. Neighboring galaxies would vanish over the horizon of visibility, leaving our local group isolated in an ever-expanding void. Fast forward to just 3 months before the finale, and solar systems would meet their doom. Stars would be ripped from their orbits, planets flung into darkness. The Sun and Earth, separated by phantom energy's relentless push, would become lonely wanderers in a disintegrating cosmos, but the worst is yet to come. Days before the end, planets themselves would unravel. Earth's gravity, no match for phantom energy's exponential strength, would lose its grip on the oceans, the atmosphere, and eventually the ground beneath our feet. Mountains would levitate, then shatter as the forces binding their molecules together fail. Then comes the atomic apocalypse. In the final horrifying minutes, even atoms' nature's unbreakable building blocks would be shredded. The strong nuclear force, which glues protons and neutrons together, would succumb. Atomic nuclei would explode like miniature fireworks, releasing all the energy stored within them. In the last microseconds, spacetime itself would fracture, dissolving the fabric of reality into a chaotic sea of disconnected particles. What's chilling is the precision of this timeline. Unlike the slow fade of the Big Freeze or the fiery collapse of the Big Crunch, the Big Rip's countdown is almost algorithmic. From galactic scales to subatomic ones, destruction follows a grim script. And here's the twist: if phantom energy exists, we might already be in the early acts of this cosmic tragedy. telescopes could one day spot galaxies straining against invisible chains, offering the first real clue that the universe's finale is written in annihilation. The question isn't just how the universe ends, it's whether we'll decipher the warning signs in time to witness its closing act. Now, let's shift our perspective from the universe's inevitable destruction to a more pressing question: could life or even intelligence outlast the Big Rip? At first glance, the idea seems laughable. If even atoms are torn apart, how could anything survive? But humanity has always defied the impossible. And here, in the face of cosmic annihilation, we find some of the most daring speculative ideas science has to offer. One radical proposal involves constructing rip-proof habitat structures designed to resist phantom energy's tearing force. Picture a civilization so advanced it engineers materials bound not by gravity or electromagnetism, but by something stronger. Theoretical physics hints at exotic matter or topological defects, quantum anomalies that might remain stable even as space-time fractures. These habitats would need to exist outside conventional physics, perhaps anchored in higher dimensions or shielded by forces we've yet to discover. It's a long shot, but not impossible. After all, black holes were once pure theory too. Then there's the multiverse escape. If our universe is one bubble in a vast cosmic foam, could we tunnel into another before the rip consumes us? The math of string theory allows for such possibilities, though the energy required would dwarf anything we can imagine. Imagine building a ship not of metal, but of warped space-time, punching through the fabric of reality to a younger, safer universe. The catch: we'd need proof the multiverse exists and a way to navigate it. Current experiments with particle colliders and quantum gravity might one day provide clues. But let's be real, these are Hail Mary passes. A more sobering truth is that survival might require abandoning biology altogether. If consciousness can be digitized, uploaded into self-repairing quantum computers, it could theoretically persist even as the physical world disintegrates. These minds would need to harness the last dregs of energy, perhaps riding the shockwaves of collapsing spacetime itself. It's a bleakly beautiful thought, intelligence lasting until the final femtosecond, witnessing the universe's last gasp. The irony: the Big Rip's inevitability could be the ultimate motivator. Faced with an expiration date, civilizations might accelerate their climb up the Kardashev scale, harnessing galaxies, then galaxy clusters, in a desperate race against time. And if they fail, well, the cosmos has a way of recycling itself. Some theories suggest the rips in point, a singularity of infinite energy, could birth a new universe. Our legacy might not be survival, but becoming the seed for something new. So, is survival possible? Maybe not in any form we'd recognize, but the deeper lesson here isn't about beating the universe's end game. It's about the staggering creativity that emerges when we stare into the abyss and refuse to blink. Now, stepping back to take a broader view, let's weigh these cosmic doomsday scenarios against each other. How do the Big Freeze, Big Crunch, and Big Rip stack up when we examine the evidence? Scientists have spent decades gathering clues, from the faint glow of the cosmic microwave background to the distant explosions of supernovas, all to answer one question: which fate is the universe actually heading toward? First, consider the Big Freeze, often seen as the frontrunner in this cosmic race. Observations of supernovas in the late 1990s revealed something shocking: the universe's expansion isn't slowing down, it's accelerating. This discovery, which earned researchers the Nobel Prize, points to dark energy's dominance, pushing galaxies apart faster and faster. The cosmic microwave background, that ancient afterglow of the Big Bang, also supports this picture, showing a universe that's geometrically flat, meaning it's likely to expand forever. If dark energy remains constant, as the Lambda-CDM model suggests, the Big Freeze becomes the default outcome, a slow fade into darkness. Then there's the Big Crunch, the dramatic comeback story where gravity finally wins. For this to happen, the universe would need enough matter, both visible and dark. to overcome dark energy's push, but measurements of cosmic density suggest we're far below that critical threshold. Even dark matter, which outweighs regular matter 5 to 1, isn't enough to reverse expansion. Some theories propose that dark energy might weaken over time, but so far, there's no observational evidence to support that. The Big Crunch isn't ruled out entirely, but it's sitting on the bench, waiting for new data to put it back in the game. Now, the Big Rip, the most violent contender, hinges on a specific flavor of dark energy called phantom energy, which grows stronger as the universe expands. If this exists, it would eventually shred everything. But here's the catch: phantom energy remains purely hypothetical. Current data fits just as well with a constant dark energy model, making the Big Rip more of a speculative outlier. That said, if future observations detect an increase in dark energy's strength, this scenario could leap to the forefront. So, where does the scientific consensus land today? Most cosmologists lean toward the Big Freeze, given the overwhelming evidence for perpetual acceleration. But science is fluid. New telescopes like the James Webb Space Telescope and upcoming dark energy surveys might tip the scales. The universe's fate isn't just a thought experiment. It's a puzzle we're actively solving, one observation at a time. And that's what makes this exploration so thrilling. Every answer leads to new questions, keeping us forever on the edge of cosmic discovery. But what is dark energy, really? This invisible force is the ultimate wild card in the universe's fate, and understanding it is like trying to grasp smoke. At its core, dark energy is the mysterious pressure that's causing the universe's expansion to speed up, not slow down as we once thought. Think of it like this: if the universe were a loaf of bread baking in the oven, dark energy would be the yeast making it rise faster and faster, stretching the dough until it's thin and cold. Now, here's where it gets fascinating. Scientists have two leading theories about how dark energy behaves. The first is the lambda-CDM model, which treats dark energy as a constant force unchanging over time, like a steady wind pushing galaxies apart. This model fits beautifully with most of our observations, from supernova data to the cosmic microwave background. If dark energy stays constant, the Big Freeze becomes almost inevitable, a slow but unstoppable march toward a dark, empty cosmos. But then there's the twist: phantom energy. This more dramatic version of dark energy doesn't just stay constant, it grows stronger as the universe expands. Picture a snowball rolling downhill, gathering speed and size until it's unstoppable. If phantom energy is real, it would eventually overwhelm gravity, electromagnetism, even the forces holding atoms together, leading to the Big Rip. The scary part: some mathematical models suggest this could happen in as little as 22 billion years, a blink of an eye on cosmic timescales. So how do we know which version of dark energy is at work? Right now, the evidence leans toward the constant lambda-CDM model, but the door is wide open for surprises. Future missions like the European Space Agency's Euclid Telescope or the Vera C. Rubin Observatory are designed to measure dark energy's behavior with unprecedented precision. Will it stay steady, or will we discover it's evolving? The answer could rewrite the universe's final chapter. Dark energy isn't just a footnote in cosmology, it's the deciding factor in whether our universe fades, crunches, or tears apart. And while we don't have all the answers yet, every new observation brings us closer to solving one of the greatest mysteries in science. One thing's certain: the universe's fate is anything but simple, and dark energy is the force pulling the strings behind the scenes. Now, let's turn our attention to the silent partner in this cosmic dance: dark matter. While dark energy is busy stretching the universe apart, dark matter is the invisible anchor, working behind the scenes to hold everything together through gravity. Imagine dark matter as the cosmic glue, binding galaxies and galaxy clusters in place, while dark energy acts like an unstoppable force trying to tear them apart. Here's the key question: Could dark matter's gravitational pull be strong enough to counteract dark energy's relentless push? The answer depends on the delicate balance between these two mysterious forces. Dark matter doesn't emit, absorb, or reflect light, but we know it exists because of its gravitational effects on visible matter. Think of it like the wind. You can't see it, but you can see the way it bends trees and moves clouds. In the same way, dark matter's gravity bends the paths of stars within galaxies and shapes the large-scale structure of the universe. If there were enough dark matter, its gravitational pull could eventually slow down the universe's expansion, or even reverse it. This would set the stage for the Big Crunch, where everything collapses back into a hot, dense singularity. Picture a rubber band stretched to its limit. If dark matter's gravity is strong enough, it could snap the universe back together. But current measurements suggest there's not nearly enough dark matter to overcome dark energy's push. Instead, it's more like a tug of war where dark energy is winning, leading us toward the big freeze. But dark matter's role isn't just about quantity, it's also about distribution. Some theories suggest that dark matter could clump together in ways we don't yet understand, creating pockets of intense gravity that might locally resist dark energy's expansion. These cosmic anomalies could, in theory, provide temporary refuges in an otherwise expanding universe, though even they wouldn't last forever. The real mystery is whether dark matter and dark energy are locked in a permanent struggle, or if one will eventually dominate. Right now, the scales tip toward dark energy, but future discoveries like detecting new forms of dark matter or uncovering hidden interactions could change everything. So while dark energy might be steering the universe toward its ultimate fate, dark matter is the unseen force that could still rewrite the ending. And as we peer deeper into the cosmos, we're not just searching for answers, we're uncovering the invisible forces that have shaped everything from the smallest galaxies to the destiny of the universe itself. Now, let's take a detour into the realm of quantum weirdness, where the rules of the universe as we know them might not apply. While dark matter and dark energy shape the cosmic tug-of-war, there's another, more unpredictable player in the game: quantum fluctuations. These tiny, random bursts of energy at the smallest scales could, in theory, rewrite the fate of the entire universe. Here's how it works. Even in what we think of as empty space, the quantum vacuum is anything but empty. It's a seething sea of virtual particles popping in and out of existence, thanks to Heisenberg's uncertainty principle. Most of the time, these fluctuations cancel each other out, leaving no lasting impact. But what if one of these flickers of energy didn't fizzle out? What if it triggered a catastrophic domino effect? Enter vacuum decay, one of the most bizarre yet scientifically plausible ways the universe could meet its end. Imagine the universe's current vacuum state. The lowest energy configuration holding reality together is like a valley in a vast landscape. It's stable, but not necessarily the most stable state possible. Some theories suggest there could be a deeper, lower energy valley lurking out there, a true vacuum. If a quantum fluctuation nudges even a tiny patch of space into this lower energy state, it could create an expanding bubble of true vacuum. This bubble would spread at the speed of light, rewriting the fundamental laws of physics as it goes. Atoms, forces, even space-time itself, everything inside the bubble would be reshaped into something utterly unrecognizable. One moment, the universe is as we know it. The next, it's gone, replaced by a new reality with entirely different rules. And we'd never see it coming because the bubble's edge would move faster than any warning signal could travel. But here's the twist: this catastrophe might not just be an ending. Some theories suggest a true vacuum bubble could spawn an entirely new universe inside it, complete with its own Big Bang. In this scenario, our universe's demise would be the birth of another, a cosmic reset button pressed by quantum chance. It's a humbling thought. The end of everything we know might just be the beginning of something else entirely. Of course, this isn't just wild speculation. The math checks out. Quantum field theory allows for this possibility, even if it's vanishingly unlikely. And while we've never observed anything like it, that doesn't mean it's impossible. After all, the universe has been around for billions of years. Who's to say it hasn't already happened somewhere in some distant galaxy? What makes this idea so fascinating is that it doesn't just override the big freeze, crunch, or rip, it sidesteps them entirely. No matter how the universe thinks it's going to end, a quantum fluke could change the script in an instant. It's the ultimate wild card, a reminder that even our most well-grounded cosmic predictions are at the mercy of the universe's deepest uncertainties. So while we keep our eyes on dark energy and dark matter, let's not forget the quantum undercurrents beneath it all. The universe's fate might not just be written in the stars, it could be hiding in the empty spaces between them, waiting for a single, random flicker to change everything. Now, let's zoom out even further, because what if our universe isn't the only one? The idea of a multiverse isn't just science fiction. It's a serious scientific possibility that could make our universe's fate feel like a single drop in an endless cosmic ocean. Imagine an infinite number of universes, each with its own unique laws of physics, its own timeline, and its own destiny. Some might freeze, others might crunch, and a few could rip apart. But in the grand scheme of things, our universe's end might not matter at all. This mind-bending concept comes from a theory called eternal inflation. Picture the early universe right after the Big Bang expanding at an unimaginable rate. Most of that expansion slowed down, giving rise to the cosmos we know. But what if some regions kept inflating forever? In those pockets, new universes could bubble up, each with its own Big Bang. Our universe might just be one of countless others in an ever-growing multiverse, like a foam of cosmic bubbles. Here's where it gets even wilder. These bubble universes wouldn't just be copies of ours. The laws of physics could be completely different in each one. Some might have stronger gravity, making stars burn out in seconds. Others might lack dark energy entirely, collapsing almost immediately. In this scenario, the fate of any single universe, whether it freezes, crunches, or rips, is just a local event, irrelevant to the multiverse as a whole. But how does this connect to eternal inflation? Think of it like a boiling pot of water. Bubbles form, grow, and collide. In the multiverse, these bubbles are entire universes, constantly being born and expanding. Some might collide, others might drift apart forever. And if our universe is just one of these bubbles, its ultimate fate becomes a small footnote in an infinitely larger story. So what does this mean for us? If the multiverse is real, it suggests that even the most catastrophic end, be it a big freeze or a big rip, isn't truly the end. There's always another universe, another chance for life, another cosmic experiment unfolding somewhere else. It's a humbling thought, but also a strangely comforting one. The universe we call home might be fleeting, but existence itself could be eternal. Of course, this raises some big questions. Could we ever detect other universes? The answer is maybe. Some theories suggest that if our universe collided with another bubble long ago, it might have left scars in the cosmic microwave background, the afterglow of the Big Bang. Scientists are actively searching for these faint imprints, like detectives looking for fingerprints at a cosmic crime scene. And then there's string theory, which takes the multiverse idea even further. It proposes that universes could exist on higher dimensional membranes or brains, floating in a vast higher dimensional space. These brains might occasionally collide, triggering new Big Bangs. In this version of the multiverse, the cycle of creation and destruction could be endless, with universes rising and falling like waves in an ocean. But here's the kicker: even if the multiverse exists, it doesn't change the reality we experience. Our universe's fate still matters to us. Whether it's heat death or a violent rip, the stakes feel enormous because this is the only cosmos we'll ever know. The multiverse theory doesn't diminish that. Instead, it gives us a new perspective, a reminder that the universe is far stranger and more vast than we can comprehend. So as we ponder the big freeze, crunch, or rip, let's not forget the bigger picture. Our universe might be headed toward one of these endings, but in the multiverse, there's no final curtain call. Just an endless cosmic dance of beginnings and endings, playing out across dimensions we can barely imagine. Now, let's rewind to the very beginning, because to understand where the universe is headed, we need to revisit how it all started. Cosmic inflation, that unimaginably brief burst of expansion just moments after the Big Bang, didn't just shape the early universe. It might have planted the seeds for everything that followed, from the galaxies we see today to the dark energy that's pulling the cosmos apart. Think of inflation like stretching a rubber sheet. In a fraction of a second, the universe expanded exponentially, smoothing out wrinkles and creating the flat, uniform cosmos we observe. But here's the twist. That same process might have left behind a hidden fingerprint: dark energy. Some theories suggest that the energy driving inflation didn't vanish completely. Instead, it could have lingered, morphing into the mysterious force now accelerating the universe's expansion. In other words, the same mechanism that jump-started the cosmos might be writing its final chapter. So how does this connect to the big freeze, crunch, or rip? If dark energy is indeed a relic of inflation, its behavior could determine which fate awaits us. If it remains constant, as the lambda-CDM model suggests, the universe will coast toward a gradual big freeze. But if it strengthens over time, becoming so-called phantom energy, the big rip becomes inevitable, tearing reality apart atom by atom. Inflation, then, isn't just a one-time event. It's the cosmic backdrop against which the universe's entire story unfolds. But inflation's legacy doesn't stop there. It also explains why the universe looks the way it does. Without that initial stretch, the cosmos would be lumpy and uneven, full of chaotic pockets where gravity clumped matter too tightly or left voids too empty. Instead, we see a remarkably smooth distribution of galaxies, a testament to inflation's balancing act. And that smoothness matters when we talk about the universe's fate. A more erratic cosmos might have collapsed long ago or torn itself apart prematurely. Inflation gave us the Goldilocks conditions for a universe that's neither too dense nor too sparse, at least for now. Here's where it gets speculative. Could inflation have also created the multiverse? If certain regions of space kept expanding while others slowed down, those eternally inflating pockets might have birthed bubble universes, each with its own physics and destiny. In this view, our universe's inflation didn't just set up its own fate. It might have spawned countless others, each on its own trajectory toward freeze, crunch, or rip. Yet for all its grandeur, inflation remains a theory, one that's incredibly hard to test. Scientists look for clues in the cosmic microwave background, hunting for faint patterns that could confirm or refute the idea. Some even propose that gravitational waves from the early universe, if detected, might carry echoes of inflation's violent birth. Until then, we're left with a tantalizing possibility. The same force that crafted the cosmos might be the architect of its demise, weaving a story that stretches from the first moments of time to the last. So as we ponder the universe's ultimate fate, remember this: whether it ends in cold silence, a fiery collapse, or a violent tear, the roots of that destiny might trace back to the very beginning. Inflation didn't just create the universe, it set the stage for everything that followed, including how it all might end. Now, let's turn our attention to one of the universe's most fascinating characters: black holes. In a big freeze scenario where galaxies fade and stars burn out, these cosmic giants would become the last survivors, clinging to existence long after everything else has vanished. But even they wouldn't last forever. Black holes are often thought of as eternal traps, swallowing everything that crosses their event horizon. Yet, thanks to the pioneering work of Stephen Hawking, we know they have an expiration date. Hawking radiation, a quantum phenomenon at the edge of a black hole, slowly chips away at its mass. Imagine a black hole not as a perfect vacuum, but as a place where pairs of particles constantly pop in and out of existence. Normally, these pairs annihilate each other instantly, but at the event horizon, one particle might fall in while the other escapes, stealing a tiny bit of the black hole's energy in the process. Over unimaginable stretches of time, this leakage causes the black hole to evaporate. The scale of this process is staggering. A typical stellar mass black hole, formed from a collapsed star, might take around 10 to the power of 67 years to evaporate completely. For supermassive black holes, like the one at the center of our galaxy, the timeline stretches to 10 to the power of 100 years or more. To put that in perspective, the current age of the universe is a mere 13.8 billion years, a blink compared to the lifespan of these cosmic titans. But what happens when a black hole finally vanishes? In its final moments, it doesn't fade quietly. As the black hole shrinks, Hawking radiation intensifies, leading to a dramatic burst of energy. Some theories suggest this could produce a flash of high-energy particles or even a mini-explosion, though no one has observed this firsthand. One intriguing possibility is that the explosion might leave behind a relic, a stable, microscopic remnant containing the black hole's original information, a nod to the ongoing puzzle of how quantum mechanics and gravity reconcile. In the context of the Big Freeze, black holes become the universe's final landmarks. Long after the last stars have died and galaxies have drifted apart, they'll still linger, their immense gravity shaping the cold, dark cosmos. Civilizations, if any still exist, might huddle near them, using their energy as a last-ditch power source. It's a haunting thought. The same objects we associate with destruction could one day be the only sources of light in an otherwise lifeless void. Yet, even they aren't permanent. As the last black holes evaporate, the universe inches closer to true heat death, a state where not even a flicker of energy remains. No motion, no structure, just an endless sea of near-absolute cold. It's a humbling reminder that nothing lasts forever, not stars, not black holes, and perhaps not even time itself. So while black holes may outlast everything else, they too are part of the universe's grand, inevitable decay. Their story, from violent birth to silent evaporation, mirrors the cosmos' own journey from fiery beginning to frozen end. As we ponder the fate of black holes in a dying universe, another profound question emerges: what happens to time itself? Entropy, the measure of disorder in a system, doesn't just shape the universe's physical end, it dictates the very arrow of time. Let's unravel this connection between entropy and time and explore whether time could come to an end in scenarios like the Big Freeze or Big Crunch. The concept of time's arrow, first proposed by physicist Arthur Eddington, ties time's forward march to the increase of entropy. Imagine a film reel of your morning coffee. Watching it play forward, you see steam rise as it cools, a natural progression toward disorder. Play it backward and it looks absurd: heat flowing into the cup, defying the laws of thermodynamics. This is entropy at work, defining the one-way direction of time. Now zoom out to the cosmic scale. In a Big Freeze, entropy reaches its maximum. All energy is evenly spread, stars are extinct, black holes have evaporated, and no more work can be done. At this point, some physicists argue time would lose its meaning. Without processes like decaying stars or orbiting planets, no before or after time might effectively stop. Philosophers call this the heat-death paradox. If nothing changes, does time even exist? The Big Crunch presents a different twist. As gravity pulls everything back into a singularity, entropy might decrease, reversing time's arrow. But here's the catch: while the universe collapses, the local experience of time for any hypothetical observers would still feel like it's moving forward. It's like being in a sinking ship. Time doesn't suddenly run backward for you, even as the universe implodes. Could time truly end? Some theories suggest yes. In the Big Freeze, the absence of change might render time a frozen variable, a relic of a more dynamic past. In the Big Crunch, the singularity could erase time entirely, resetting the cosmic clock. Meanwhile, quantum gravity theories propose that time might emerge from deeper, timeless physics, meaning it could dissolve back into that fundamental layer when the universe reaches its extremes. For now, these ideas remain tantalizing speculation, but they remind us that time isn't just a backdrop, it's woven into the universe's fate. Whether it stretches into silence or collapses into nothingness, entropy holds the key. And as we peer into the abyss of deep time, one thing is certain: the universe's final chapters will rewrite the rules of reality itself. Next, we'll explore how cyclic cosmology offers a dramatic escape from this grim fate. What if the universe doesn't end but reboots? But what if the universe doesn't truly end? Imagine a cosmic cycle where every collapse sparks a new beginning. This is the heart of cyclic cosmology, a riveting twist on the universe's fate that turns doom into rebirth. Here, the Big Crunch isn't a finale, it's a reset button, compressing everything back into a singularity only to explode outward once more in a fresh Big Bang. The idea of an oscillating universe isn't new. Pioneering physicists like Richard Tolman toyed with it nearly a century ago, suggesting that gravity's pull could reverse expansion, crunching the universe down until conditions are ripe for another explosive rebirth. Picture a cosmic accordion, expanding and contracting endlessly, with each cycle lasting billions of years. So, what's the evidence? Supporters point to the universe's near-perfect balance of matter and energy, a flat geometry that teeters between eternal expansion and eventual collapse. Some theories even propose that dark energy, the force driving expansion, might weaken over time, allowing gravity to claw everything back. Others speculate that quantum fluctuations in the crunch's final moments could trigger a new bang, like a phoenix rising from ashes. But cyclic cosmology faces hurdles. For one, entropy. Each cycle would add more disorder, meaning subsequent universes might look wildly different from ours. There's also the issue of observational silence. We've found no echoes of a prior universe in the cosmic microwave background, no scars from past collapses. And while string theory offers mathematical elegance for cycles via colliding branes in higher dimensions, it's still untested, yet the allure persists. A cyclic universe dodges the bleakness of heat death or cosmic rip, offering immortality on a grand scale. It's a poetic vision, civilizations rising and falling across eons, each cycle unaware of the last. Could our universe be one page in an infinite cosmic book? For now, it's a captivating what if, one that keeps physicists searching for clues in the void. Next, we'll see how string theory's extra dimensions might rewrite the rules entirely, offering escape hatches from oblivion. Now, let's stretch our imaginations even further into the world of string theory, where the universe's fate might not be bound by the rules we think we know. This isn't just about 3 dimensions of space and 1 of time. String theory proposes that tiny, vibrating strings underlie all matter, dancing in as many as 10 or 11 dimensions. These hidden dimensions, curled up at scales smaller than atoms, could rewrite the cosmic rulebook entirely. One of the most striking ideas from string theory is the concept of branes, short for membranes. Picture our universe as a 3-dimensional brane, floating in a higher dimensional space, like a sheet of paper suspended in a vast room. Other branes might exist nearby, invisible to us but exerting gravitational pull or even colliding with ours. Such a collision could have sparked our own Big Bang and might one day trigger another, offering a cyclical universe without the entropy problems of traditional cyclic cosmology. Then there's compactification, the process by which extra dimensions are folded up so tightly we never notice them. The shape of these compact dimensions isn't arbitrary. It determines the laws of physics in our visible universe. Change the folding pattern, and you might alter dark energy's strength or gravity's grip, tipping the scales toward a big crunch, rip, or freeze. Some models even suggest that compact dimensions could unravel in the far future, drastically shifting how the universe evolves. String theory also opens doors to wilder escapes. If our brain is one of many in a multiverse, could civilizations hop to younger, more hospitable universes as ours decays? Or might higher dimensional physics reveal ways to stabilize dark energy, preventing a big rip? These ideas border on science fiction, but they're grounded in equations, however untested they remain. Critics argue that string theory's lack of experimental proof keeps it in the realm of speculation. Yet its mathematical elegance keeps physicists hooked. Whether it's brains colliding, dimensions unfurling, or strings vibrating in unseen ways, string theory reminds us that the universe's fate might be far stranger and more malleable than we've dared to dream. Up next, we'll explore how the holographic principle suggests that even as our three-dimensional universe fades, its essence might endure, written on a two-dimensional boundary like a cosmic save file. Now, let's step into one of the most mind-bending ideas in modern physics, the holographic principle. Imagine if everything we see, touch, and experience in our three-dimensional world is actually encoded on a distant two-dimensional surface like a cosmic projection. It sounds like science fiction, but this radical theory could redefine how we understand the universe's fate, especially as it decays into darkness. The idea stems from black hole thermodynamics. When matter falls into a black hole, it seems to vanish forever, violating a fundamental rule of physics: information can't be destroyed. But in the 1970s, physicist Jacob Bekenstein calculated that a black hole's entropy, or disorder, is proportional to the area of its event horizon, not its volume. This was a clue. The information about everything swallowed by the black hole might be stored on its surface, not lost inside. Decades later, Leonard Susskind and Gerard T. Hooft took this further, proposing that the entire universe could work the same way. Our three-dimensional reality, with its galaxies and atoms, might just be a holographic projection of data written on a distant two-dimensional boundary. Picture it like this: a movie screen displays a three-dimensional image, but the actual data is stored flat on the film. Similarly, the universe's information, every star, every thought, every law of physics, could be etched onto a faraway surface we'll never see. This isn't just a quirky analogy. In 1997, physicist Juan Maldacena mathematically proved a version of this idea, showing how a higher dimensional space could perfectly correspond to a lower dimensional boundary, like a cosmic dictionary translating between dimensions. What does this mean for the universe's end? In a big freeze, as space stretches into cold emptiness, the holographic principle suggests that information about everything that ever existed might still be preserved, just in a form we can't access. Even if protons decay and black holes evaporate, the script of reality could remain intact on that two-dimensional surface. Some theories even propose that a future civilization could, in principle, reconstruct the entire universe from this data, like rebooting a computer from a backup file. But here's the twist: if the holographic principle is true, it challenges our very notion of space and time. The three-dimensional world we perceive might be an illusion, a shadow of deeper physics playing out on a distant frontier. As the universe races toward its fate, whether a freeze, crunch, or rip, the holographic principle offers a strange comfort: that in some form, the story of existence might never truly be erased. This leaves us with one last cosmic mystery to unravel. If our universe is a simulation, could its end just be someone hitting the off switch? That's where we're headed next. Now, let's take a step into one of the most provocative questions in modern cosmology. What if our universe isn't real? Simulation theory suggests that everything we know, from galaxies to consciousness, might just be lines of code in an advanced civilization's computer. If that's true, then the ultimate fate of the universe could be as simple as someone pressing delete or restart. This idea isn't just sci-fi speculation. Philosopher Nick Bostrom formalized the argument in 2003, outlining three possibilities. Either advanced civilizations never reach the technological level to run ancestor simulations, they choose not to, or we are almost certainly living in one. The logic hinges on computing power. If future civilizations could simulate minds as complex as ours, they'd likely create countless simulations, making it statistically probable we're in one. Elon Musk and other tech leaders have echoed this, pointing out how rapidly our own simulations, like video games, are advancing toward realism. But what would a simulated end look like? In a big freeze scenario, the program might simply keep running until all energy dissipates, like a screensaver fading to black. A big crunch could be a deliberate reset, an intentional reboot to start the simulation anew. The most unsettling is the big rip, where the simulators pull the plug abruptly, deleting the cosmic hard drive in an instant. Some physicists argue that glitches in quantum mechanics, like the uncertainty principle, could be artifacts of finite processing power, hints that reality has a pixelated limit. There are scientific angles too. If the universe is a simulation, its laws might resemble optimized code. The speed of light, a processing speed limit. Quantum entanglement, data linking separate parts of the program. Even the holographic principle we just discussed fits neatly. A two-dimensional boundary storing three-dimensional data is exactly how efficient simulations compress information. Philosophically, this raises eerie questions. If our universe is simulated, is its end meaningful or just a developer's whim? Could civilizations like ours, nearing simulation capabilities, be shut down to prevent competition? Or is the universe programmed to end precisely to study how intelligent life reacts to doom? Yet for all its intrigue, simulation theory has critics. Some physicists point out there's no observable evidence, no pixels in spacetime, no cosmic error messages. Others argue that simulating every particle's quantum state would require unfathomable energy, making it impractical even for advanced beings. So where does that leave us? Whether metaphor or reality, simulation theory reframes the universe's fate as something malleable, even artificial. It challenges us to ask if existence is code, does its end erase us or just pause the game? Next, we'll shift from digital doom to humanity's real-world survival strategies across eons. How might our descendants outlast the cosmos itself? That's where the story gets inventive. Let's pivot from pondering the universe's end to something even more daring: how humanity might defy it. Picture this: trillions of years from now, long after stars fade and galaxies drift apart, our descendants could still be thriving. Far from passive observers, they might engineer survival on a scale we can barely imagine. One audacious idea: Dyson spheres, megastructures built around stars to harness every drop of their energy. Imagine a shell of solar panels encircling the sun, capturing its output to power supercomputers, cities, or even entire civilizations. Physicist Freeman Dyson proposed this in the 1960s, not as a blueprint but as a thought experiment. Today, scientists scan the cosmos for infrared signatures that might betray these colossal constructs. If advanced civilizations exist, they'd likely need such energy farms to survive the universe's inevitable cooling. But building one would require dismantling planets Mercury's metals, Jupiter's gases, transforming raw materials into a stellar power grid. Then there's mind uploading, the notion that consciousness could be digitized, freeing us from fragile biological bodies. Think of it as backing up your brain's data into a quantum supercomputer. This digital existence would sidestep entropy's toll: no aging, no disease, just pure thought persisting in energy-efficient servers. Some theorists suggest we'd inhabit virtual paradises, crafting realities where heat death is irrelevant. Others warn of existential risks. Would a copied you truly be you? And could these digital minds avoid corruption over cosmic timescales? But what if escape is the ultimate solution? Enter universe migration. If our cosmos is doomed, perhaps future civilizations could tunnel into younger, hotter universes through hypothetical wormholes or quantum bridges. String theory hints at multiverses with varying physical laws. Some might be life-friendly eternally. The catch: we'd need to master physics far beyond Einstein's dreams, manipulating spacetime like putty. Each of these leaps sounds like sci-fi, yet they're grounded in real science. Dyson spheres align with thermodynamics. Mind uploading emerges from neuroscience and computing advances. Universe hopping, while speculative, isn't ruled out by quantum gravity models. The common thread: survival isn't about resisting cosmic fate, it's about rewriting the rules. Critics argue these are fantasies, diverting attention from Earth's pressing crises. But history shows humanity's knack for turning wild ideas into reality: flight, moon landings, the internet. Why not stellar engineering or digital immortality? Here's the thrilling part: the first steps are already underway. AI research edges toward artificial consciousness. Breakthroughs in fusion energy could preview Dyson tech. Even our telescopes hunt for alien megastructures. The ultimate legacy of intelligent life might not be monuments, but a refusal to vanish quietly into the dark. Next, we confront an even thornier question. Should we meddle with the universe's fate, or would playing cosmic architect unleash unintended horrors? Now let's step into the moral maze of universe-scale engineering. The idea of reshaping cosmic destiny is exhilarating, but it's also fraught with ethical dilemmas. Should humanity, a species that's barely mastered its own planet, dare to tinker with the fundamental forces of existence? Consider the risks. Tampering with dark energy to avoid a big rip, for example, might unravel spacetime itself. Imagine pressing a cosmic undo button only to trigger a chain reaction we can't control. The same physics that could let us engineer a softer fate might also amplify chaos. Even Dyson spheres, seemingly benign energy harvesters, could destabilize stellar systems if mishandled. A single miscalculation might snuff out a star prematurely, dooming any planets that relied on its light. And what if our megastructures inadvertently broadcast our location to hostile civilizations? The universe may be vast, but not everyone out there might share our survival goals. Then there's the fairness question. If a privileged few upload their minds or flee to a younger universe, what happens to the rest? Would cosmic engineering deepen inequalities, creating a rift between those who can cheat entropy and those left behind in a dying cosmos? History shows how technological divides breed conflict. Now scale that to interstellar proportions. Philosophers argue that manipulating the universe's fate isn't just a scientific challenge. It's a moral test of whether we can act as stewards, not conquerors. Yet the counterargument is compelling. Doing nothing might be the gravest sin of all. If life is rare and precious, isn't it our duty to preserve it? Some scientists compare cosmic engineering to medicine, intervening to save a patient. The universe, in this view, is a ticking clock, and our ingenuity is the only cure. After all, nature isn't inherently fair. Supernovas don't ask permission to sterilize nearby planets. Why should we hesitate to level the playing field? The debate echoes in today's labs. Climate geoengineering, like spraying aerosols to cool Earth, is a microcosm of these cosmic ethics. Small-scale tinkering already sparks fears of unintended consequences. Scaling up to galaxies magnifies the stakes exponentially. Perhaps the wisest path is humility. Before bending the cosmos to our will, we'd need consensus on what better even means. More time, more diversity, more happiness. These aren't just physics problems, they're reflections of our values. The ultimate fate of the universe might hinge not just on equations, but on whether we can answer one profound question: what kind of legacy is worth fighting for? Next, we'll see how cultures across history have envisioned the end. and how those myths eerily align with modern science. Now, let us turn our gaze to the stories humanity has told about beginnings and endings long before telescopes peered into the cosmos. Across cultures and centuries, myths and religions have grappled with the same question science now explores. Strikingly, many ancient visions of the universe's fate echo, or eerily foreshadow, modern theories like the Big Freeze, Big Crunch, or Big Rip. Take Norse mythology's Ragnarok, a cataclysmic battle where gods and giants perish, stars vanish, and the world drowns in fire and ice before rebirth. It mirrors the violent chaos of a Big Rip, while the cyclical rebirth aligns with theories of a bouncing universe. Hinduism, too, speaks of cosmic cycles, Brahma's days and nights where universes dissolve and reform endlessly, akin to a big crunch followed by a new Big Bang. Even the Buddhist concept of kalpas, vast epochs ending in destruction and renewal, resonates with oscillating universe models. Then there's the Hopi prophecy of the end times, where the world grows cold and dark, echoing the entropy-driven Big Freeze. The Abrahamic faiths, from Christianity's Book of Revelation to Islamic eschatology, describe a universe winding down, stars falling, heavens rolled up like a scroll. These images parallel a contracting cosmos or heat death, though often layered with divine judgment absent from scientific narratives, but contrasts are just as revealing. Science frames the universe's fate as inevitable physics, devoid of purpose or morality. Many myths, however, infuse the end with meaning, a test, a punishment, or a transition to something transcendent. The Aztec belief in 5 suns, each era destroyed by gods to create anew, suggests intentionality foreign to astrophysics. Similarly, the Maori story of Ranginui and Papatuanuku, where the separation of sky and earth births the world, personifies cosmic forces science describes mathematically. What's remarkable is how these ancient intuitions sometimes align with cutting-edge cosmology. The Maya long count calendar, obsessed with cyclical time, hinted at universe-scale repetition millennia before physicists debated cyclic models. Meanwhile, the Jain cosmological model, with its infinite, self-renewing universe, uncannily resembles modern multiverse theories. Yet science and myth diverge sharply in one respect: evidence. While myths rely on revelation or tradition, cosmology demands data. The cosmic microwave background isn't prophecy, it's a measurable echo of the Big Bang. Dark energy's pull isn't a deity's will but a phenomenon we quantify. Perhaps the deepest lesson lies in the human impulse to seek patterns. Whether through scripture or equations, we're driven to make sense of infinity. And in that shared quest, even stark contrasts between gods and gravity, rebirth and entropy reveal a profound truth. The universe's fate isn't just a scientific puzzle. It's a mirror reflecting our timeless need to find meaning in the stars. Next, we'll see how artists and storytellers have imagined these cosmic endings, from haunting paintings to blockbuster films. Now consider how artists and creators have translated these cosmic doomsdays into stories and images that grip our imagination. From the haunting beauty of paintings to the high-stakes drama of blockbuster films, art offers us a lens to visualize the unthinkable, the end of everything. Take the 1979 sci-fi classic The Black Hole, where a doomed spacecraft spirals into oblivion, mirroring the relentless pull of a collapsing universe. The film's eerie final scene, with characters trapped in a surreal, hellish landscape, captures the existential dread of a big crunch. Decades later, Interstellar painted a more hopeful yet equally terrifying vision, blending science with speculation. The Tesseract sequence, where time folds like origami, hints at higher dimensional physics that might one day defy entropy. Meanwhile, Melancholia Lars von Trier's masterpiece frames a rogue planet's collision with Earth as a meditation on despair and acceptance, evoking the inevitability of cosmic endings. Literature, too, has wrestled with these themes. H.G. Wells' The Time Machine closes with a distant future where the sun dims and life clings to a freezing Earth, a chilling echo of the Big Freeze. In The Three-Body Problem, Liu Cixin imagines civilizations desperate to escape a collapsing universe, flipping the script on humanity's survival instincts. Even poetry leans into the void. T.S. Eliot's The Hollow Men whispers, "This is the way the world ends, not with a bang but a whimper, distilling the Big Freeze into a single shuddering line." Visual artists push these ideas further. The abstract swirls of Zdzisław Beksinski's dystopian paintings feel ripped from a universe unraveling in a big rip, while Anselm Kiefer's monumental canvases strewn with ash and lead evoke the weight of cosmic decay. Then there's The Great Red Dragon by William Blake, where apocalyptic fury mirrors the violence of a collapsing or tearing cosmos. Even video games like Destiny weave these theories into lore, with the heat death of the universe as a recurring villain. What makes these depictions so compelling is their emotional honesty. Science gives us equations, but art gives us goosebumps. When Doctor Who portrays the last star flickering out, or Ad Astra shows an astronaut adrift in an indifferent cosmos, they tap into our deepest fears, not just of dying, but of being forgotten. The Hubble Space Telescope's images of dying stars are breathtaking, but it's Star Trek's Big Goodbye holodeck episode where characters grapple with digital eternity that makes us ask, what legacy survives the heat death? Yet art also rebels against despair. Hayao Miyazaki's Nausicaa of the Valley of the Wind ends with life reborn from toxic ruins, a defiant nod to cyclical universes. And in All Tomorrows, Nemo Ramjet's speculative evolution saga shows humanity's descendants thriving in bizarre forms billions of years hence, a playful middle finger to entropy. These creative visions do more than entertain. They bridge the gap between equations and empathy, letting us feel the universe's fate in our bones. Whether it's the operatic doom of Goethe Dämmerung or the quiet desolation of The Road, art reminds us that the cosmos's end isn't just physics, it's poetry. Next, we'll tackle the myths and misunderstandings that cloud our view of the universe's ultimate destiny. Now, let's clear up some of the biggest misunderstandings swirling around the universe's ultimate fate. It's easy to get tangled in myths, especially when talking about something as vast and abstract as cosmic endings. So let's separate fact from fiction and shine a light on what science really tells us. First up, the idea that the Big Crunch is a guaranteed outcome. This myth often stems from early 20th century cosmology, when scientists assumed gravity would eventually reverse the universe's expansion. But here's the twist: dark energy changed everything. Observations over the past few decades show that the universe isn't just expanding, it's accelerating. Unless dark energy weakens or reverses something current evidence doesn't support, the Big Crunch becomes increasingly unlikely. Then there's entropy. Some assume it means the universe will simply run out of energy like a battery dying. But entropy is more nuanced. It's about energy becoming so evenly spread that no work can be done, no stars burning, no life thriving. Think of it like a cup of coffee left on the counter. It doesn't disappear, but it cools until it's the same temperature as the room. That's the Big Freeze, a universe where everything reaches equilibrium, not emptiness. Another common mix-up, the Big Rip is often framed as dark energy winning over gravity. While that's partly true, the real wild card is phantom energy, a hypothetical form of dark energy that grows stronger over time. Without phantom energy's extreme repulsive force, ordinary dark energy would just keep the universe expanding, not tearing it apart atom by atom. And let's tackle the myth that black holes are cosmic vacuum cleaners destined to swallow everything. In reality, even black holes aren't eternal. Thanks to Hawking radiation, they'll eventually evaporate over unimaginable timescales, yes, but they're not the final chapter. Finally, some think these theories are set in stone. They're not. Our understanding is still evolving, shaped by new data from telescopes like the James Webb Space Telescope. Maybe dark energy behaves differently than we think, or undiscovered physics could rewrite the rules entirely. The universe's fate isn't a done deal, it's a puzzle we're still piecing together. So next time you hear a sweeping claim about how it all ends, remember, the cosmos loves surprises. What we know today might just be the prologue to a far stranger story. And speaking of cutting-edge discoveries, upcoming missions could revolutionize our predictions, but that's a topic for another segment. But here's where things get truly exciting, because the answers we're searching for might be just over the horizon, thanks to a new generation of cosmic detectives. Cutting-edge telescopes and missions are gearing up to peel back the layers of the universe's greatest mystery, its ultimate fate. Let's take a closer look at the tools that could rewrite our cosmic storybook. First, the James Webb Space Telescope is already revolutionizing our view of the cosmos. Unlike its predecessor Hubble, Webb operates in infrared, allowing it to peer through cosmic dust and spot the faintest, most distant galaxies. Why does that matter? By mapping how these early galaxies formed and moved, Webb could reveal whether dark energy has always behaved the same way, or if it's changing, which would tilt the scales toward a big crunch or rip. Then there's LISA, the Laser Interferometer Space Antenna, set to launch in the 2030s. While Webb studies light, LISA listens for gravitational waves, ripples in space-time caused by colossal events like merging black holes. These waves could be our key to understanding dark energy's true nature. If LISA detects patterns suggesting dark energy grows stronger over time, phantom energy, the Big Rip scenario suddenly becomes far more plausible. But wait, there's more. The Vera C. Rubin Observatory, with its massive mirror and wide field camera, will scan the entire southern sky every few nights. By tracking billions of galaxies, it could spot subtle distortions in their shapes caused by dark matter's gravitational tug. That data might finally answer whether there's enough matter to pull the universe back together, or if dark energy's push will win out. And let's not forget the Euclid mission, Europe's Dark Universe Explorer. Euclid's precision mapping of galaxy clusters and cosmic voids could expose cracks in our current models. Maybe dark energy isn't uniform. What if it's patchy, like Swiss cheese, that would upend everything? Even wilder ideas are on the table. Projects like the Square Kilometre Array, a radio telescope network, might uncover primordial gravitational waves from the Big Bang itself. These ancient echoes could hint at whether our universe is one of many in a multiverse, a twist that would make our local fate just a footnote in a grander saga. The best part, these missions don't work in isolation. Data from Webb, LISA, Rubin, and others will converge like pieces of a puzzle. Each one narrows the possibilities, bringing us closer to knowing whether we're headed for a freeze, a crunch, or a rip. And who knows, maybe they'll reveal an entirely unexpected ending. After all, the universe has a habit of surprising us. So while we don't have all the answers yet, one thing's certain: the next decade of cosmic exploration will be anything but quiet. The tools are ready, the questions are sharp, and the universe, it's waiting to spill its secrets. Now, as we stand at the edge of this cosmic journey, let's take a moment to reflect on the sheer magnitude of what we've explored. The universe's fate isn't just a distant scientific curiosity, it's a story that stretches across timescales so vast they dwarf human history. Whether it's the slow, silent fade of the Big Freeze, the dramatic collapse of the Big Crunch, or the violent shredding of the Big Rip, each scenario paints a picture of existence that's both humbling and electrifying. These aren't just theories, they're potential final chapters written in the language of physics, waiting for us to decode them. What's truly remarkable is how these possibilities force us to confront our place in the cosmos. In the face of a big freeze where entropy wins and all energy dissipates, we're reminded of the fragile, fleeting nature of life. Yet, even in that cold, dark void, there's a strange beauty, a universe that ran its course, leaving behind echoes of what once was. The Big Crunch, on the other hand, offers a poetic symmetry, a universe that collapses back into the singularity from which it sprang, perhaps birthing a new cosmos in the process. And then there's the Big Rip, a cosmic crescendo where everything, from galaxies to atoms, is torn apart in a finale of unimaginable force. But here's the twist: no matter which fate awaits us, the journey to uncover it is what makes humanity extraordinary. We're the universe's way of understanding itself, peering into the darkness with telescopes and equations, turning mysteries into knowledge. The fact that we can even contemplate these scenarios, let alone test them with missions like Webb and Lisa, is a testament to our curiosity and resilience. So as we close this chapter, I'll leave you with this: the universe's end is inevitable, but its story isn't just about endings. It's about the questions we ask, the discoveries we make, and the legacy we leave in the cosmic ledger. Whether we're stardust today or scattered atoms tomorrow, our quest to understand the cosmos binds us to something greater. So keep looking up, keep wondering, and remember, you're part of a story that spans billions of years. And who knows, maybe the next great cosmic revelation will come from you. If you've enjoyed this journey through time and space, don't forget to hit that like button, subscribe for more deep dives into the universe's greatest mysteries, and ring the bell so you never miss an update. The cosmos is full of secrets, and together we'll keep uncovering them, one star, one theory, one mind-blowing discovery at a time. Thanks for joining me on this adventure, and until next time, stay curious.